All right, everyone. It'll be around a 3-hour session. It's led by Kartik. Kartik is 2018 grad from NIT Surat. He worked at a startup. ਪਹਿਲੇ worked at HSBC, then he worked at a startup. Now is currently working remotely. The class today is going to be around mostly LLMs, their current state. Kartik currently in his day job is doing a lot of MLOps, deploying machine learning models. He's been doing it for a while now. So he'll take us through, how do you train a model and a bunch of other things. When slides dekhi to let me not speak on his behalf. But extremely experienced guy. So if you have more questions later, feel free to come. It'll be around a 3-hour session. Let's keep it interactive. If you have questions, let us know. Feel free to interrupt beach mein. If you have, anything, agar fast ja raha hai, slow ja raha hai, let us know. With that, Kartik, over to you.
Okay, so how many of you guys know MLOps? No one? That's nice. And then LLMs? How many of you have heard LLMs kya hota hai? Right. Okay, like what is an LLM? Large language models, right? Okay. And LLMs ke liye APIs use kiye kisi ne? Has anyone used like ChatGPT, Anthropic, cloud-based models or anything, right? Projects mein use kiya hoga sabne, right? Okay. So you guys would be knowing ki last 2-3 years mein there's a lot of development in LLM space, right? And there's a reason what has led to this point. So we had classical machine learning, but now we are into more heavy into LLMs. And there's a reason for it. This talk is mostly going to be a little bit advanced, right? So we'll discuss LLMs, but not the basic foundational stuff like ChatGPT kaise use karna hai, how to create a REST API with ChatGPT and all that. It'll be more in depth on how LLMs work, right? What you have to do to train your own LLMs to improve its quality and all that. Okay. So what we'll do is, see, this is how it's going to be. Starting May, we would be covering very easy beginner level stuff, right? And slowly we'll go really fast. Okay. Ab isme, what will happen is eventually we'll speed up a lot. Kafi kuch samajh nahi aayega. If you get 10% out of it, that's more than enough, right? The main agenda is not to make a very simple, easy REST API based stuff, but to actually let you guys know ki what is there in this whole space, right? What is happening? You'll then get to know these keywords, and then in your free time, you can search and, you can dive deeper into these things. Ye clear hai sabko? So it's okay if you don't understand much, but maybe if you have any doubts, whatever it is, feel free to ask, right? All these PPTs and codes would be shared baad mein, to aisa kuch nahi hai that you have to take pictures or anything, right? Okay. We can start. So, do anyone know there was a paper called "Attention is All You Need" by Google, right? There was this paper by 8 guys. What they did was they created a new kind of ML model that is known as a transformer. Transformer became really popular. The first deployment type was called BERT. BERT was used in Google. Us time pe speech to speech and all that AI jazz was coming in, right? Us time pe Google Home was recently introduced, and we were having that, and you can chat with it, and it was really next level stuff. Okay. So that was launched in June 2017. Then June 2018, there was also another company called OpenAI. So OpenAI took the same concept, this ML model known as a transformer, and then they started working deeper into it, as in key what all changes could be done, because this was open sourced. So they created something called GPT, which is called generative pre-trained transformers. We'll go deeper ki wo kya hota hai, what is it, right? But when they did it, it gave some really good improvements. But at the same time, OpenAI was focused on, does anyone of you know Dota game, right? Yeah, you guys have played Dota, right? So there was this one match between Dota and AI. Do you know this guy called Dendi? Dendi is a very famous world champion Dota player, right? So OpenAI defeated that guy using their own algorithms, ek time pe, and then after 1 year or 2 years something, they defeated the world champion team at that point using their AI. So they were very good in reinforcement learning stuff, and they were somewhat good in transformer-based language stuff as well, right? So OpenAI was also focusing on a lot of stuff at that time. What happened was, in November 22, they launched, after close to like 3 years, after 3 years, they launched something called ChatGPT. And we all know ChatGPT, right? In the first 5 days, it got like 1 million daily active users, and now it's like multiple millions of people using it every day. And not just ChatGPT, but other models, right? So there's a lot that has changed, right? Don't look at much into the model architecture or whatever, but this is what the transformer architecture was when it was proposed in 2017, right? And this is what the architecture looked like. And it had a very special thing. That special thing is called attention. Does anyone of you guys know what attention is? सुना है कभी LLMs में attention? हरकिरत? Hmm. Yeah, exactly. So what happens in attention is the distribution between words. So basically, it's a model which predicts the next word, but the attention mechanism gives a lot of importance to all the words, how all the words are interconnected with each other, right? This is the equation. This is literally the equation of attention. This is the thing that makes LLM so special, basically. And this is what makes it different than all the classical algorithms. So there's something called Q, K, and V, right? Now, Q is your sentence, what you're giving. ML may, we guys know, right? There's something called weights, model weights, right? So K and V are some weight matrices, which is learned by the ML model. Now, what happens is a combination of Q, K, V, if you do a matrix multiplication followed by a softmax and then multiplied with another matrix known as V, you get something called an attention. And this is how attention looks like. So you'll see there's a sentence, and you can see how every word in the sentence is related to other words. And it's a weighted matrix, as in you can find out how much every word depends on other words, right? So in a way, this was really good because it can give deeper understanding of a sentence to the model. इससे पहले nothing like this was there, where a given sentence, every word's dependency to all the other were calculated in some way. It was used to predict something, right? So on the right, this is what attention looks like. Basically, this is a matrix where the matrix is a square matrix. At every side you have these words and then the weightage of each word with each other. Basically, that's what attention is. This is what it looks like in architecture. Attention may I had this small equation, right? If you want to actually do that equation is literally this. You take the Q vector, then you have K and then V, and then you have to do the same math in code to finally get the attention value. Now these weights, what does that mean? Basically, this is what the model learns. It's not defined that it should be something that humans can also understand, right? So that's what actually weights are. Basically, it's a machine's representation of the data such that it's able to get the final output. It can solve for the final output it's trained for, right? So these weights can mean multiple things. And this is one attention heads. Then you can combine multiple attention heads. So basically, these weights are just one version. You can create 10 different versions, and then these are extra 10 types of weights. What every head looks for, we don't know. Maybe there's one head which looks for all the adjectives, one head which focuses more on what's happening in the future or in the back, or what's the nouns or activities that's happening in the sentence. We don't know what these weights are, but somehow if you create multiple weights, the model learns better because it knows the sentence even better now. Clear ho raha hai thoda idea? Good. Feel free to ask questions though. Okay, so some burning questions. Why LLMs are a separate field now, right? Why don't we consider transformers as an algorithm in machine learning, right? We have CNNs, random forest, MLP, multi-layer perceptrons, and we have a lot of these things, cat boost and all these coming up. But still we give LLMs a really different field, a different importance. Like, why is that? Like, does anyone know? Any guess? Why is LLM a completely separate field now? I mean, Kalko, if I'll say Node.js is a new library, you still use it in full stack development, right? Kalko, Node.js ke log are not completely different than all the full stack people. What makes LLM different? That's one thing. Second question is, do you guys know what CI/CD is? What is DevOps? See, me at your age, I knew what DevOps was, to be honest. College final year. So you take these containers and then you know how to continuously integrate together a team to make changes to the code. Then you have, let's say, a container or a package, then you deploy it in multiple platforms. The whole thing together is known as a CI/CD platform, right? Also, this field is known as DevOps, where you have like additional things like how to monitor these things and all of that. That is what DevOps is. There's a field in DevOps called MLOps, which is DevOps specifically for machine learning, because in machine learning you have to do a lot of extra things. Feature engineering is there, deployment ke baad you have to look for the weights, redeployment and all that. But these days we are starting to say LLM ops also. Have you guys noticed we say LLM ops, not ML ops or DevOps per se? So that's also something new that's coming up. See, in the same way, if you have a JS Docker container in your DevOps, you can't say it JS ops or whatever, right? LLMs are still given its importance key. This is specifically LLM ops, and this is MLOps. Okay, the third is, what has changed in the traditional way of working with ML models? Can anyone answer this one? Is there something that has changed fundamentally? Has anyone worked with any previous ML models? CNNs use की होंगे object detection के लिए, right? Yeah. Perfect. Yeah. I mean, no, it's true. Yeah. Someone. Yeah. Exactly. Hmm. Yeah. So both the answers are correct. Previously, there was a lot of supervised ML model work, right? You should have a well-labeled data set. You'll fit your model to that data set, and there would be output. LLMs, in a lot of ways, you don't need a proper labeled data set beforehand. That's one of the biggest changes, the shift that has happened in ML. So here are some of the answers to those questions. One is, how has training changed, right? Classical ML say LLM ops ka training, how has it changed? So we are training multi-billion parameters now, right? All the previous ones used to be in millions. Some of them were even less than millions. The training was actually expensive, but the whole model was small. And so training ke time pe you had to like look through a lot of things. For example, Markov trees or whatever, right? You have to go through a lot of solutions, but the final tree which is created is pretty small. Then you have to just traverse the tree to get your output. Random forest, gradient boosting, these were all models like that. Is LLMs ke andar, they are like multi-billion parameters, right? These are huge models with GBs and GBs of weight, like 200 GBs, 150, 40, 80, right? These kind of weights. And the second thing which you guys mentioned is training mostly on unsupervised data, right? Uh, data set, having a data set was something that was really hard to actually create, right? Then to have a big enough data set that the model learns and all of that. There were some of the improvements done by OpenAI, specifically where in GPT, the first GPT that came in, they emphasized key we don't need a trained data to actually train an LLM. What you can actually do is, if you have lots and lots of text, you can then create a generative pre-trained format in which just by that text you can train the model, right? So now the data game is solved. You just have to put a lot of compute into it, and the model should be big enough to learn everything, right? If there's a small model, no matter how much data you give it, the learning caps. But over here, the data problem is solved, and now you have computation, which these companies don't have. I mean, they have thousands of these clusters of GPUs with them. So they just need now a big model so that they'll put all that data and compute together, and the model would give really good results, right? And that's why LLMs came into picture. That now you can just take Wikipedia data sets and then start training, and then it will work. Okay, so that's for training. For deployment, a deployment is CPU versus GPU. Previously, you'll train a lot of ML models on GPUs, but during deployment, you can deploy it on CPU, right? So training was costly, but deployment was easy. You just have to deploy it on CPU. These days, you can't actually deploy on CPU. I mean, you can, but for large scale and big models, still you need a GPU, right? And so now training also happens on GPUs, and then inference, the deployment also GPUs are preferred. And then maintaining models is huge. All the parameter weights of a 70 billion parameter model would be like 40 GB, 10 GB, 20 GB, right? And then if you're training, there are multiple of these weights created. How would you save it? How would you manage it? How would you train these models? So these are also some of the challenges people face. Then the biggest thing, performance, right? There was a paper. Has anyone read the paper called Few Shot Prompting? Something related to that. You guys know what prompting is? We know, right? Way back when the Chat GPT thing came up, there was this paper which defined that you don't need to train your model on a problem set. You can ask it questions and it'll give answers. So few short me, you'll give some examples and ask the question. it'll give you the answer. So the way we do prompt engineering, it was kind of explaining prompt engineering thing. The biggest advantage of doing this is I didn't train anything. I'm just teaching it how to answer properly and I'm getting my stuff done, right? So that is what the zero shot and few shot means. Zero shot as in key, I'm just asking the question, it's giving the answer, nothing. Few shot is some examples. I ask the question, based on all the context, it is able to give answers. But in both of these ways, we are not training anything. We are just using the model and it's giving us answers. Okay. Okay. So this was one of the biggest achievement of LLMs. Then new techniques to help LLMs. Previously, we didn't have RAG-based pipelines. I mean, we were having a lot of vector databases, and vector databases was used hugely in recommendation engines and everything, right? We didn't knew it. Now it's a very common field called RAG, retrieval augmented generation. You take a vector database, put some context. Based on that embedding, you fetch some values and you get the context, right? So RAG is something new. जो LLMs में is very common. And then you have better analysis for prompting. You have multiple methods now. There are new courses these days called prompt engineering, right? That you can take, and then it'll teach you 20 different ways to say the model what you want to get, and then without training anything, you can get the answers, right? Okay, let's see how many of you are comfortable up till this point. Sab samajh aa raha hai? ठीक है? Questions? Any questions? Yeah. Multilayer perceptrons are neural networks. Oh, natural language processing is like the broader field of anything that has to do with text. So text could be multilingual text, and then what you want to do with that text could be multiple things. You want to do named entity recognition, right? So that is one thing you want to get out of it. You want to do translation of one text to another language. That's another thing. You want to structure it properly or whatever. So NLP is like the broader high level describing everything. So it consists of all the classical models also. LLMs also comes under NLP only. I mean text-based LLMs. There are also vision transformers, which is like same transformer, but image input and something output, right? Okay. Any other question, guys? Yeah. Okay, what weights are? Fine. So basically you want, so there are X and Y. X is your question, Y is your answer. And then you have a mathematical equation. So hota hai na, X equals to Y plus 5. You put a value of X and then you have to find the value of Y. You can find the value of Y, X minus 5, right? Like this. So Y find ho gaya abhi. Let's say what I'll do is, I can't find Y, right? Why I can't find Y is because I don't know how to find Y, basically. I can't model the question into an equation. You know X equals to Y plus 5, but what if you don't even know the equation? Then what would you do, right? So at the end, all of these things are just simple mathematical equations. What you will do now is, I will take a model with some random weights, and I'll try to train it in a way that when all the multiplication and sigmoid sab kuch ho jata hai, the final output is one of the classes. So if it's a cat dog predictor, weights would be something that after all the multiplication with weights, it can say if it's a cat or a dog. Initially, these weights would be some random numbers. Now you want to adjust these numbers in such a way that the final answer would automatically be cat or dog, right? So these are weights, and then you just train it. When you train it, they take some numerical form, which can finally give you the output, which is your classification image, for example. Clear? Hmm. How that works, say, I meant was, see, humans think in 3D. Can you think in 4D? No, right? So this is known as like features. So 3D we can think, 4D we cannot, 5D we cannot. But in ML, what we do is we take 100 different n values, right? So 100 n mein 100th n pe kya chal raha hai, we don't know. But these are some numbers which are able to meet the end goal. The end goal now is final answer, cat hai ya dog hai, right? That we want to predict. So it doesn't mean that ki un weights ka kuch specific meaning hona hi chahiye, right? It can be anything, but it gets the job done. It is actually optimized in a way that it's giving the answers. Somewhat clear? Okay. Any other questions, guys? Yeah. Yeah, they do. That's why the number of layers they have, the number of heads they have, these are like multiple dimensions to an LLM. Yeah, good question. Yeah. Yes. Yeah. So it's kind of like you have to first create an architecture. Us architecture mein, whatever you want to do, you'll add stuff. You'll add, subtract in a way such that the architecture is optimized, right? I mean, it shouldn't be too bulky, too big, not being able to do. So these are some random stuff done by researchers, right? They'll experiment with multiple heads. Now, these days, what is happening is weights itne bade ho gaye hain that they are actually grouping stuff together, right? Like 5 layers should share one head. The next 5 should, it's called like grouped query attention. Like you're grouping all the queries together because the number of weights are in billions. So you're trying to optimize it. Llama suna hoga, right? Llama 2 is actually a grouped query attention based model. Okay. Good question. Anything else, guys? Continue करें. समझ आ रहा है थोड़ा थोड़ा? थोड़ा थोड़ा भी बहुत है. ठीक है? The actual goal is get all these keywords and then you can search later on if you want to dive deeper into this LLM field. ठीक है? Okay, so let's focus on accuracy. ठीक है? Let's go into how these LLMs work. You have an input, which is what is. It goes to the LLM. LLMs are next token predictors, not next word. These are tokens, right? Token could be half word or whatever. So next token is predicted, which is what is the. The goes back, you match it with what is. So what is the new output now. And then it predicts the next thing. What is the best? Then you have to combine what is the best, give it again. What is the best place? You have to keep doing it again and again in cycles. It will just, at every turn, it will output one token, right? So these are basic LLMs. And when you get the output inside the server, you run these cycles. जब तक there is a EOS token, known as end of sequence token, which means कि अब sentence खत्म हो गया, answer is खत्म हो गया, you can give it back to the user, right? That's what the cycles are for. Okay, so you would have seen all these parameters in APIs, right? Hyperparameter, not hyperparameter, sorry, temperature. These are called hyperparameters, but don't mix it with like the training hyperparameters and all. These are hyperparams that you can use to get a better output. So top P, top K, and then some seed values, right? So what temperature means is the more temperature value will give, the more creative the model would be. It's because the final words that it has to select from, if the higher is the temperature, the more the randomness. So the more the creative thinking, artistic way of doing it, right? So let's set the temperature to 0 if you want your application to be very deterministic. हर बार मेरा output change नहीं होना चाहिए to the given input, right? So set it to 0. Then you know top P is top, search for the keyword after from top P percentage values, and then top K is get the top K number of selections and then randomly select between them, right? Seed is, does anyone know what seed is in ML? So yeah, randomness is something like, obviously nothing is truly random. So what you also do is, for randomness, you can also give certain values to actually change the random output also. These things are called seeds, right? If you fix a seed, there's a high probability that the next time when you ask the random number generator, it will still give you the same random number, right? Because the way it's using the seeds. So seed, basically, if you, some APIs would give you the option to fix a seed. If you do that, then also it's a high chance that the model would output the same thing. Even if you fix temperature or seed, can you guarantee the output of LLMs by APIs? So we are talking ChatGPT, Claude, or all these things. If you fix a temperature, which is 0, don't be creative, always give the same answer. I fix a seed value so that their random number generators are also in tune. Would I still get always the same input? If I give the same output, I'll get back. Do you guys think so? Okay, yeah. So it's not the case. Still, a lot of APIs, they don't guarantee that if you fix these parameters, you'll still get, but the chances become really high. Like 99% of the time, you'll get the same value, right? Okay. So parameters are in billions. Mostly the bigger, the better. So if you want high accuracy, always start by the biggest models, right? The APIs of the biggest models. And then when you see really good output, you can then choose for the smaller versions. That's the basic stuff, because the reason is these APIs are really cheap now, right? So $2.5 for 1 million input token. In 1 million, you can just put in like multiple books, right? So it's totally fine. 2.5 is nothing, right? And then output is $10 per million output tokens, right? This is also not that expensive now. And this is the price for Claude 3.5 Sonnet by Anthropic. The guy at Anthropic actually used to work before at OpenAI. He then left OpenAI to create his own company, right? Anthropic, and then they created this model called Claude. And Claude is also now competing with OpenAI in a lot of places. Okay, clear, guys? Yeah. Since during training, and hyperparameters are also there during training. We call it hyperparameters. They should not actually be hyperparameters, to be honest. But then after the training, everything is done, after the deployment happens, that's when you have these hyperparameters. How? These hyperparameters. Okay, so what happens is you have the output, you have like multiple output tokens, right? So do you know, like, humans have a vocabulary, right? English may we know 200 words, right? So they also have a fixed vocabulary. Whenever a next token is printed, they'll tell you the probability that which next word is the highest out of those vocabulary words, right? Ab wo highest, you don't always want that highest only, because you want to be creative. Every time you ask for it, it should have different answers. So which means the highest should never be selected. It should be one among the highest, right? In a way, if you want to be more creative. So the next 5 words in that sentence, it'll pick one of them and will create a story from there. Thoda clear hua? Okay. All right. So we have a field called prompt engineering. Iske andar you'll get to know a lot of ways just to give questions to the LLMs and you'll get answers, right? I would just say there are some really good blog posts on multiple different types of prompt engineering, right? And so probably it'll be good if you, rather than taking a full 10-hour course teaching prompt engineering, you just go through 2 blog posts and you're done with it, right? Okay. So iske andar you have, it's an example over here that you can do something called chain of thought. So on the left, you have Roger has 5 tennis balls, he buys 2. It's a simple math problem, right? And the final question is, how many tennis balls does he have now, right? The answer is he has 11. The math was actually not right by the LLM. And so the next thing you can actually do is you can say that Roger has 5 tennis balls. How many tennis balls does he have now? Then you can actually ask, you can actually give the answer, right? And when you give the answer, you can say Roger started with 5 balls, then 2 cans, 3 tennis plus equals to this. And then you can ask the question. Now, LM is also going to answer in the same way. It will actually break the question step by step. It will also now try to answer it step by step. And in that step by step thing, it will actually answer better output. And most of the time, mathematically correct, right? So in a way, we didn't do anything. We just changed the way we defined the question and we have a proper answer now. So that's a way of prompting. In the same way, you have few shots. So on the right, you have classify the sentiment as positive, negative, or neutral. So let's say you have YouTube comment section detector or something, right? That you can say this percentage is positive, negative, neutral. These are the top comments, right? Stuff like that. How would you do it? You just ask the LLM. This is the first comment. This was positive, this was negative, this was neutral. So it is defining what exactly this means. And then you can ask your comment and then ask it to be positive, negative, neutral, right? Otherwise, it can start answer anything. If you want, like, let's say answer in 1 word, you can just say at the end that, answer in 1 word, okay, or whatever. So these are some very simple ways of doing prompt engineering. You can just use it. Then you also have something called tags and personas. So to actually explain the model really well, where your code starts, where your article starts, where the headlines are and all that, right? Start creating these tags. So the article tag start and end, and then mentioning the article tag in the prompt, the first system generation prompt, would really help the model to know what is the question, what's the data, and how to generate the answers, right? So yeah, this is what prompt engineering is. So you guys would have heard what RAG is, right? When do we use RAG? Like, why do we use RAG? Yeah, context. Yeah, context documents you want to give it. Okay, and yeah, yeah. So during training, they also had a fixed cutoff knowledge. They don't know about it. It's your, let's say you are in your organization, it doesn't have any knowledge about your org. You just give it all the context of your organizations. You put it in a vector database. The vector DB does something called an embedding search by using some policy. Basically, all you're trying to do is before calling the LLM, you're giving it all the context, and then using that context, it should answer it, right? So this is RAG. So second thing to increase accuracy that you should do is to actually give it better context into the thing. So you have a lot of tools which can, let's say if you're answering a QA bot or something, right? If for a given text field, you can now go to Wikipedia, grab some documents for that field, and then give it along with your prompt. This would help the model really well to, finally be able to answer it, right? So things like that you can do. So this is RAG. Okay. This might be, okay, let's see what we can do. Do you guys know how to like evaluate LLMs? Okay, that's fine. So let's say I want to define accuracy. If it's a cat dog predictor, I can just know if it's a cat or a dog, right? So based on how many cats were detected, dog were detected, we have a accuracy score that is done. But LLMs actually generate sentences. Now, how would you rate if two sentences better than, right, the other one, or is the sentence correct or not, and all that? So we have certain metrics. Let's not go deeper into what these metrics are, but there are metrics called ROJ and blur, right? These metrics really help you to find out how good the answers were if you have a test data set. Basically, you had your questions and answers. You can train it, and then you can check if the answer generated and this generated, how much the words are similar, n grams together, like words, how many they are similar, and then it generates a numerical value, and then you can use that value to know how good your LLM is doing. So basically, there are metrics in which you can also see if the LLM output is good or not. थोड़ा थोड़ा clear हो रहा है? Okay, nice. Then you also have data sets. So if I want to create a math question answering like check का कुछ copy बनाना है मुझे, right? Which can just give math question answers really well, right? The first model I'll actually do, let's say if I want to create my own model or whatever, is to actually go to data sets, publicly available data sets, and see who does the best on that particular data set. So for example, math. So math is high school level competition problems gathered from several sources. So it's a data set of math questions. So all the LLMs would show you performance on this data set. You choose the best one, right? So in this way, if you have a problem and if you can find the similar data set, and then you can see which LLM is actually doing the best in that, and then there's going to be high chances that this LLM would do the best on that particular data set. Okay, for that, you can go to chat LMYS, which is the LM Arena. Right over here, you can see. Do you guys know what chatbot arena is? Does anyone know? Okay, so what started happening was they wanted to know how good humans think these outputs are. So this is a general common poll where anyone can come and the LM output would be generated, and then they can choose which one they liked more. And in this rating system, the final arena leaderboard is decided. So these days, the Gemini model is doing really well, right? In general, people like this model more, the output generated by this model more. Then what you can do is go to these category. These are different languages, data sets, and all that. You can select, for example, math, and then I can see O1 preview does the best, right? O1 2024. And in this way, I can figure out which actually LLM to use from out of all the available options because I know these data sets. Okay. Then you also have Hugging Face LLM leaderboard. In this leaderboard also, you can select, you can go to advanced filters. You can select how big model you want, how many billion parameters, and then you can also see what type of model and then what kind of data set it should do well on, right? Okay. And then based on it, you can choose which is the best model you want to use and start using that for your LLMs. Okay. Now, once you're not, I mean, if you have done RAG, you've selected the best LLMs, you're able to generate these outputs, right? If still you don't get a good accuracy, that's when you have to go for training, right? Otherwise, the first thing to always do is to actually go for these things, to optimize on all of them. And then if these things don't work out really well, is when we go for training. Okay, okay guys, questions till this point? यहाँ से आगे सब कुछ थोड़ा advanced हो जाएगा, which is fine as I said. But questions till this point? Should we go ahead? समझ आ रहा है? थोड़ा थोड़ा आ रहा है? That's also enough. Just remember these keywords. Okay. So we have a lot of open source models. So 1 billion parameters takes 4 bytes, right? Or 32 bits. So 1 billion parameter would be 4 GB of VRAM. So in our PCs, we have CPU, RAM, and then GPU. And GPU's memory is called VRAM, right? So it's that RAM, not your PC's RAM. And so 1 billion parameter is going to take 4 GB RAM. Now you guys would know CPU ki RAM is easy, cheap, but GPU RAMs are expensive, right? All these models, I think RTX 50 is launched now with I think 32 GB or 24 as the RAM. 24. It's 24, I guess. And so that is launched, and then you just have 32 GB for like for a GPU which costs 1.5 lakhs or something, right? So these are expensive RAM. And so 4 GB of RAM is needed for 1 billion parameter model to host over there. And so does anyone know Llama ke kitne variants available hai of how many billion parameters? You have a 7 or 8K model, then you have a 13 one, then you also have a 71, then you also have a 400 one, right? So to run a 7 billion parameter model, you need 28 GB of space, which you don't have, right? Because it's pretty expensive. And so in this way, you have to do a lot of things to be able to run these LLMs also. Okay? So that's the thing. Let's see AWS. How many of you guys have worked with AWS? Right? Oh, that's very nice, to be honest. Okay. So in AWS, you have an instance called P4D.24x large. The instance has 96 CPU cores, and it has 1200, almost 1.2 TB of CPU, and then it has 8 A100 GPUs, right? Which is a 40 GB GPU card, and 8 of them makes 320 GBs. Then you have 320 GBs, and the cost for per hour is $32. So which means if you just host a 70 B Llama, it will cost you almost 20 lakh rupees per month just to host one model, right? And you need multiple models for a lot of users, right? You can't just deploy one version of it, because then all of them would bombard on this one server. The server would just heat up, right? You need multiple of them. So that's why LLMs hosting them is super expensive. It depends. Load testing se pata chalega. Plus, it also depends what the client wants. Let's say you give me a question and you're okay ki main kal answer karu, right? So I'll find a way to batch it. I'll do something around it, but it's a shared thing between like how fast the client wants, right? And then, so in this way, you can handle multiple users because now you're going to do it for the whole day. So you have a lot of capacity. So in this way, but concurrency, if you'll say, so it depends from model to model, right? And is concurrency ko increase karne ke liye bhi there are multiple stuff which we are going to discuss baad mein. Okay? That's a nice question. Anyone else, guys? Okay, let's continue. Okay, so this was around training 1 billion parameter, 4 GB of space, right? Now, if this was actually deployment, now if we'll discuss about training. So during training, for one parameter of the model, you need 2 additional optimizer states. You need 1 additional gradients. So these are some of the variables for training, right? And then you need 2 additional activation and temporary memories and all. So basically training may you have to store extra things, right? During training and then to train these models. So what actually ends up happening is that for one parameter, you actually need a total of 6 parameters during training. To be able to train that one parameter, you need additional 6 parameters in that particular GPU. So which means that 4 GB weight, which was 1 billion, is now 24 GB, right? Which means that training may you need even 6 times more GPU capacity. Hosting was already 20 lakhs per server, right? That we saw. And now you need 6x more to be able to train a full-fledged model. That's why full fine-tuning is not something we do, right? So that's why full fine-tuning is to these giants, OpenAI, Facebook, Meta, Anthropic, and all these companies which are coming in, they actually do a full fine tuning. Just they train every single billion parameter model for days and days, right? But we never fully fine tune. And that's the reason it's super expensive to be able to do that. Clear, guys? Okay. So what are the issues? Large memory size, which we discussed, maintaining and deploying multiple models. All of this we are doing just for one model. You need multiple of them. And if you end up experimenting, then तुम्हें पता नहीं कितने experiment models भी साथ में चलाने हैं, right? So that's super expensive. There's also something called catastrophic forgetting, right? If you will start training on one type of data set, it'll start forgetting the other things. It won't do that well, right? You have to generalize it really well, basically. So if you'll start to fully fine tune a model, an existing model, it'll start to forget and do poor and other things because now it's specializing on that one task, right? Okay. So for that, to be able to train our own LLMs, first you have to get an open source LLM, right? Not the closed source ones, they are not available. So I get an open source model, let's say a Llama 3B, a Llama 7B model or something like that, right? And then I want to fine tune it. I want to fine tune it on my data set. And so now I can do a training. Now there are multiple ways you can do training without actually spending all that cost, right? And so there are a lot of techniques to be able to train these models. Why are we training these models? Because RAG didn't work really well. We tried a lot of prompt engineering. We tried the best models available, right? We still think that now training can actually improve stuff. That's why we are now going into training mode, right? And so for training, we have something called parameter efficient fine tuning. We are fine tuning it, but it is parameter efficient. So less number of parameters we are going to tune, which will take less RAM. That much RAM we have available somehow, and then we are able to actually train the data set on our given models. Clear, guys? So PEFT there are multiple different algorithms by which you can train, right? So there's something called SFT, supervised fine tuning. There's something called RLHF. Has anyone worked with reinforcement learning based algorithms? So Super Mario खेलने वाले games खेले होंगे ना, मतलब the AI learns Super Mario. So it's kind of like you give it a platform, you tell a policy to optimize, and then all these variables you define, and then you just leave it to actually do a lot of computations, learn every step, and then be able to do good at that. That's called reinforcement learning. Okay, so you can do RLHF. There are other things also, PPO, which optimizes on not having to do RLHF or whatever. But at the end of the day, there are multiple algorithms which you can use to fine tune. The best one, the easiest one is actually to do a supervised fine tuning, SFT, right? And the variant of SFT, one of them is known as 𝗲𝗁, which is this. And then we have another variant which is known as prompt tuning. So we have 𝗲𝗁. This is from SFT, which is supervised fine tuning. So in both of these, we have data available, right? We have a proper data which we want to train on. And the two types of SFT is this. Is it visible now? Yeah. Okay. So prompt tuning, what we do is we create additional parameters. So one thing we do for sure is we freeze the whole model. Do you know what model freezing is? That you are going to use the model, but the weights cannot be changed by you. And what fine tuning is you want to change the weights so that the final output is better to your answer or what you want to get it done, right? What you want the model to do. Thoda clear hai? So if you freeze the model, what you actually end up doing is you take some less number of parameters that you actually want to train. Because freezing ke time pe, you don't have these additional 6 parameters, right? For those frozen models, because you don't want to change their values. And so for the small subset of parameters you're going to change, un sab ke liye the additional 6 states would be created, and that's why you're saving on all of those parameters. Okay. So SFT mein we have something called prompt tuning. What you do is you introduce some additional parameters input mein, right? So you have the prompt, you give it the prompt input mein you add additional weights. These are randomized weights, right? And then you get the output. And how you train a model, you take the output, you know the answer of that output, you calculate something called a loss, right? That's the loss policy you have, and then you backtrack it. Basically, you adjust the weights in such a way that it should now actually answer in your particular output format, right? So in a way, you are correcting it again and again, and this is how you're actually training a model. all the time looking at its output, you know the right output, you calculate the loss, you tell all the weights up to until back what you should have changed to actually give this output, right? But in this one, everything is purple, which means you don't actually change the weights. But you will change the weights for these things. These the additional parameters that you have introduced, right? These are the random parameters in input that you have introduced. And then you have LoRa weights, which is like this is your transformer. And then you're going to add some additional weights, but for additional weights, first you train it. How do you train it? You give the input, then you pass the input through LoRa weights, and then you also pass it through transformer. And then you get the output. And then output aa jaane ke baad, what you do is you back propagate, but you don't change the transformer weights. You only change the additional LoRa weights, the thing in yellow that you have added. And this, then finally LoRa weight you can add with your transformer. And what ends up happening is your weights are now fine-tuned for your data set. Clear hai thoda? Now, obviously, the size over here is the same because the dimension is the same. But this doesn't mean that the LoRa weights are exactly equal dimension to the transformers, because then purpose is defeat ho gaya, right? You have a 5 million billion parameter model and then you have additional 5 billion parameter weights. So this is generally like 5 to 10% of the whole billion parameter model. So some few millions or something like that, right? Clear hai thoda thoda? So this is what SFT is. And let's discuss LoRa more. So how this thing actually happens, why is it like this, is you have two matrices. These are the decomposition matrices. So ये हम सब ने 10th में किया था ना matrices. उसमें if you have D cross R and then you do a cross multiplication with R cross N, you actually end up with D cross N, right? Now, if you'll see the number of parameters over here plus the number of parameters over here, right, are way less. And then if you multiply it, you get a weight, right? So you have to create these two matrices such that when you multiply it, they actually match up with the transformer weights, right? So these two matrices, right, if you do D cross R plus R cross N, these would be very less number of parameters that you have to train, right? But then finally you can get the same weight matrix that you can add to your transformer and then you can train it. Clear hua thoda thoda, right? These weights are very less, very small. So that's why you get the added benefit that the number of parameters are less. Okay, we won't go too much deeper into what this is. Basically, what's the advantage is now you can train a 7 to 10 billion parameter model on your consumer GPU, a 24 GB GPU, which was not possible before, right? That's the whole agenda of doing LoRa. Okay. And scores, research shows that scores are comparable to full fine tuning. Full matlab you would have actually done this thing over here, which costed 20 lakhs, right? You are doing a full fine training. The actual results are comparable to that. There's very small drop. If you will see the research paper, LoRa has its own research paper. It's actually by Microsoft, who invented this technique. One of the researcher actually invented LoRa in Microsoft, and then he open sourced the whole implementation for it. Okay, so yeah, and so now using this, you can train a 7 to 10 billion parameter model, and there's no added latency if you actually add it with the transformer. So see, the number of multiplications would be my input goes into this matrix, there's some multiplication over here. Then the same multiplication is over here. Then I add it, right? And then I get the output. What if I just add it beforehand? Transformer plus layer becomes the final this transformer. And so number of multiplications are less now, right? So in a way, if you merge LoRa layers with the transformer, you don't have now additional latency, additional addition of compute. So jitna zyada compute badhega, utna time lagega output mein, right? So now LoRa actually doesn't add to the latency. The latency is still the same. So we've got the added advantage of a lot of things, right? Almost full fine tuning wali speed hai. There's no speed drop. Accuracy also increases. We can use our commercial GPUs to do it. Guys, clear itna? Thoda tough hai? Okay, it's fine. You'll have this PPT. You can search for these on end, right? And then you can know there are a lot of blog posts which are created for all this. So it'll make it easier, but it's really important to actually for you guys to know what LoRa is on the first place, right? And then you can dig deeper into it. to actually implement all this is very easy. In Hugging Face, you have like everything in like 2 lines of code, right? If you want to do LoRa, there's an SFT line in 15 lines. You can just train your own LLM models and all that, right? So actual implementation is pretty smooth. Yeah. Question. You do a 2 plus 2 equals 4. It's literally the same simple addition. Yeah. It's freeze during training, but once you're freezing it because you don't want the additional 6 parameters per parameter, right? You're freezing it because you need the model's output, and then you also want your random weights, and then the output, you need the difference. You know what the improvement is because you know the final answer. You calculate the loss now. To be able to calculate the loss, you should know what the model currently says. Then you would say, you have said this, but I want this. Then I calculate the loss, which is the error the model actually did. Then this error I propagate back, right? So I want the model to run to be able to get this so that I can train the weights, the additional weights that I've added. Okay. Any other question, guys? Continue, kare. Okay. So we have something called model quantization, right? Now, why to spend a lot of the time? You see a lot in images, right? If you have a sky image, most of the stuff is blue only, right? And then when you compress it, there are these algorithms which are lossy and lossless. You know what's the difference? Lossy, lossless compression algorithms. Yeah, perfect. So what you try to do, there are multiple algorithms which find pattern in these images. So instead of doing like, let's say 200 blue pixels, it will just finally say this is like 200 times this pixel at these positions, right? Something it'll do. Lossy means that if you'll compress and you'll decompress, you won't see the same exact pixel to pixel values, right? And lossless is you'll get the lossless compression. Obviously, lossy compressions are way better than lossless. But in a way, what you're trying to do is you actually decrease the data, the whole data set. You found a lot of things which are just redundant, you decreased it. Same kind of thing you can do in LLMs also, right? What if for one parameter, which was 32 bits, what if I'll start saying, ki, okay, I'll just remove all the bits and I'll make it 2 bytes, which is 16 bits, or I'll make it 1 byte, which is 8 bits. So instead of pi की value taking anywhere to we want, हमने हमेशा g की value 9.8 ली है, right? कभी कभी 10 ले लेते हैं because it's easy. 3.14 pi keeps on ending. So what you actually do is truncate it at a value. What you get is almost the same as what you would have got 3.5 key really high values, right? So the same you can do in these LLMs is if instead of using full 32 bits, if you cut it short into 16 bits, or there's something called brain float also. What does is the dynamic range is a bit high. Let's not get into this, but what you can do is decrease the number of bits. So storage is less now. So the initial 1 billion parameter equals to 4 GB can now be 1 billion parameter equals to 1 GB if I divide 32 bits by 4, which is 8 bits, which is 1 byte, right? So the same model weights, I'll convert it into 1 byte 8-bit format, and then the memory would be less. Simple, right? Okay, so in this way, you can fit a bigger model easily into these consumer GPUs. In terms of accuracy, things actually drop, right? Because all these multiplications, the final answer is different than the reduced ones. But you do see significant drop after 16 bits. So 32 to 16, you kind of get the mostly the same output. From 16 to 8, you see a lot. And then from 8 to 1 bit is literally one parameter is represented as an integer. So that's like huge drop in accuracy. ठीक है, ये clear हुआ? So then you have quantization. To do it, there are multiple libraries. One of the libraries known as bits and bytes. Right? You can just use it to quantize it. It's in Hugging Face. You just need one line to quantize your model. There's also something called activation aware quantization, in which what happens is all these bits that we have, you want to actually cut some of the bits, keep it in 32, but some of them you want in 1 byte, some you want in bits and all, right? What happens is the final weights are really high in accuracy now, rather than you mindlessly just cutting down on the number of bytes. Okay? Okay, so that is what AWQ is, activation aware. So you kind of train things in such a way that the quantization part that you have, right? You actually decide which weights are more important for the answer, and then you keep it the same. The ones that actually doesn't contribute much to the answer, you decrease it short. And in this way, you're saving on memory and you're able to put the whole LLM into GPU. Okay. Yeah. So what if I'll do LoRa with quantization? Like LoRa se kya hua? I can now take the model, I can fine tune it and then deploy. And quantization se kya hua? Memory aur kam ho gaya, right? So there's something called Q-LoRa, which uses both LoRa. This is your trained model adapters, and then you have quantization, and you can mix it both to create these servers which can fit into your GPU and also give you fast results. Okay, guys, questions till this point? Fine. Let's have some questions then. Okay, what is AWQ, if anyone can explain again? Hmm. Yeah. Hmm. Yeah. Right. Yeah. Right. Okay, so that's what AWQ is. And why do we do it? Why do we do quantization though? To reduce the size. But what will also reduce if the size reduces? The accuracy is also going to drop, right? Okay. So you have something called LoRa adapters. First is LoRa exactly are these two matrices. Obviously, they are not exactly two in matrix. They have multiple matrices, but the thing is these weights, which when multiply becomes this, and then you somehow add it with your transformer, right? This dimension are the same. So these are the LoRa weights. What is a LoRa weight then? You had a data set, you trained for that data set, right? So I had a coding, I had a code data set, right? I want to create an LLM which really helps me in coding. So I have the data set with all the GitHub scrape that I did. Now I'm training on that. So these weights are going to help the model to be able to be a better coder, right? So now I have the same general transformer model. I have the same llama, but now I have some additional weights. If I add it to llama, it becomes a better code editor, right? Or basically a code complete or whatever. So these are the additional weights. So you have multiple of these weights, and then you can actually train these things on multiple other tasks that you have, right? So this is what LoRa weights are. So there are a lot of trained adapters also if you want, right? So one thing is by this company called Predibase. Over there, you can have a lot of LoRa adapters. And then as we discussed that this thing has to be the same, right? There should be a transformer, and the training is done for that specific transformer weights. So you cannot take any LoRa adapter, Llama say you trained it, but now you are mixing it with Mistral. You can't do that, right? So you finally take this. Okay, yeah. You can train your own. Otherwise, you also have something like this, right? So this is trained on summarization. There are a lot of adapters, and you have to choose an adapter based on what you want to actually do. There would be multiple adapters over here. You'd also get to know that this adapter is trained on Mistral. So the base model has to be Mistral, but then you can add this adapter and you can also compare the result. That without the LoRa, this is the output, right? And this is the base model output without LoRa, and then with LoRa, this is the output. You can see side by side that, without your weights versus with weights, how it's doing. And then all of these weights are available in Hugging Face. So if you have some question and maybe there is a LoRa based weight available on Hugging Face to solve the same thing. So you don't have to do all the training and everything, right? You can also search for PEFT, which is PEFT on Hugging Face. If you do that, then you would actually find adapter for all these things. When you read the description, you'll get to know that this LoRa adapter is trained for this data set. So now I can use it with this model to actually solve my problem, right? So a lot of trained adapters are available online. You can search it through PEFT, and then you can use it for your training. Okay, and then obviously you can train your own adapters, right? The adapters are also small in size. So if the model weights for Llama are 40 GB, your adapter would still end up being, some MBs, few MBs, right? So that's also something you're saving on. Okay. Okay, guys. Clear up till this point? Any questions? No? Should we continue? Okay. Should we take a short break? Yeah? Okay, we can stop for 5 minutes, I guess. And we'll start again. Yeah? We are starting with inference and cost optimization, right? Okay. Let's see. What is inference? Does anyone know inference kya hota hai? Yeah? Okay. Prediction, right? Sorry? Okay, nice. Yes? Predicting, yeah, right. Anyone else? What is inference? Making conclusions, okay. Okay, inference is you give input to the LLM, it gives you output, right? That is when you actually deploy it for the final use. Inference is when you get the prediction out from these LLMs. That is simply known as inference now. So inference is going to cost a lot, right? And then inference is also slow. Why does it cost a lot? Because these models are huge. And then they need GPUs. GPUs also multi-GB. Then so you need to have some big servers. And that's why it costs so much. And that's why you have to now see how you should deploy these models into production so that you can save on cost, number one. And you can also save on speed. These are billion parameter models. A lot of math goes into the multiplication, right? A lot of compute goes into it. And due to that, the speed is also slow, right? Your Python code versus an LLM inference. Obviously, the LLM inference has way more calculations, right? So this is what is going to be about. What are the things that is happening in LLMs for the speed and cost optimizations of it? Okay, clear? Okay. Output, yeah. Okay. Yeah, ये visible है? Okay, we saw this example where we will give as input what is, we get the, then we give a new input, what is the, right? Over here, from here, then it gives best. You add it again, you get place, right? In this way, you're adding stuff again and again, but if you'll see what is was computed first, the whole math happened in the LLM, then there was the output the. When you do what is the whole computation happens again, which is what is ka computation would also happen and the's computation would also happen, right? So you see a clear pattern over here that all these things are just same compute happening everywhere. So you know caching, right? In caching, what do? Something is pre-computed, right? Or something you already know the answer for, you put it aside so that it can be used again. And that saves you a lot of sometimes computation, sometimes speed and things like that, right? And so you can use it here as well. This thing is known as a KV cache, right? And so let's see how KV cache works. There are two phases of a KV cache. KV kya tha? Does anyone remember now what was K and what was V? Exactly, weight matrices. Attention weight matrices, right? You had QKV in which Q was your query, the question you asked. And K and V were the weight matrices that you trained. And that's why it's also known as a KV cache. Because all the weight matrices output, you're actually caching it. Where does this cache is saved? Kahan ye cache kidhar saved hai? Generally, where is your cache saved when you do run a Python code? Server तो मतलब सब कुछ ही हो गया. I mean, in a way, I live in India, but I also live in Delhi, right? Yeah. Which RAM? VRAM, right? So, like the time it is going to take from saving your cache to RAM for GPU to actually go to that RAM would be way more expensive. So the cache it's going to use is inside, internal to the GPU. That's why the KV cache lives inside the GPU, right? And now let's see how it works. There are two phases. One phase is known as a prefill phase, and another one is a decode phase. So the red one over here is a prefill, the green is a decode. These are two different states the LLM is operating on. In prefill, what happens is what is goes inside, the first big computation happens. Like what is the do word hai, but you have a big prompt, right? All of that mathematical computation happens, and then you save it in the KV cache. And then what does the LLM do? It predicts the next word, which is the, right? Now, what is ka whole computation is saved into the KV cache? and the is also computed. It's also given as output. Then you see the over here, right? Now when the goes in, initially you wanted what is the, right? What is already available in KV cache now, right? You're not going to now calculate again all the matrix multiplication for what is. You just need to do the multiplication for the, and the rest of the matrices are taken from the KV cache. Simple. And when you do this, yahan pe the biggest thing was the computation that used to happen. Itna sara multiplication used to happen to do the first matrix multiplication. Yahan pe you just want to do the matrix multiplication for this last token, not the whole prompt, right? So if it's a book that you have given as the context, it's the last word now. The whole book is done in the first phase, which is the prefill phase. Okay, so then the goes in, cache is used, best is used, then the is also cached with KV, right? Now the KV cache has what is the, best goes here, best goes in input. What is the is already available. Best ke liye we compute again. What is the best place, right? This is how now computation happens. Clear hai ye? Exactly. वो अगले phase, prefill is the process when you actually do the biggest computation and you save it. So first, when you get a question, it's a big like 200 line question. So you do for the whole 200 line, you'll do the math. Then 200 lines are saved, and then those 200 lines generates one final word as well. That word would be given again. 200 का computation happened for the first time. That only that time is known as the prefill. बाद में फिर prefill नहीं होता. Then the, you calculate the, save the again, because you have now the matrices for the. Next token भी predict हो जाता है. You take that token, then you calculate for that token in that way, right? So prefill only happens once, but decode keeps on happening again and again, right? Prefill is very heavy on compute, and decode is heavy on memory. Why is decode heavy on memory? It has to save a lot of KV cache, right? Decode में और next words generate होते रहेंगे, KV cache में जाता रहेगा, KV cache भरता रहेगा, और these memory, GPU memory is very expensive, right? And so if you have these long context sentences, तुम्हारा cache, the whole GPU will start to actually overload with all these RAM that is being used. So you get the usual out of memory errors and all that, right? Yeah. नहीं वो नहीं होगा. So okay, that model knows कि क्या last में था, क्या next में था. ऐसा कुछ नहीं है. There's a loop that is created, right? वैसे loops भी होते हैं. That's why you always have max number of tokens that you want as output, and then you also have EOS token, which is like you stop at this moment now, right? And then you also have something like some similar words and keywords you can give that if these keywords come in, you stop. So stuff like that is also there. Okay, and just to make sure that happens. But good question. Okay, okay guys, should we move ahead? LLMs have two phases, prefill and decode. They have a KV cache. Something is compute expensive, something is memory expensive. Okay. Now let's understand the LLM inference. Okay. So models take token as input. There is a thing called latency versus throughput versus bandwidth. Okay. Okay. So bandwidth kya hua? We have this router over here. It has a maximum speed that it can transfer. Let's say it's 2 Gbps. But it doesn't mean 2 Gbps is now flowing also through these wires, right? It also depends how much this whole class is using, right? So that's why bandwidth is the max capacity of the network. Throughput is actually the data which is flowing, which is how much are we using now. We collectively are using, let's say, 50 Mbps. So bandwidth would be, let's say, 2 Gbps. We are using 50 Mbps. That's the throughput. And latency is the time it is going to take. Latency in this case for LLMs is, I did an input, how much time it is taking to get the output back, the round trip basically, right? So these are the three things: latency, throughput, bandwidth. Then you have the LLM inference. You have something, a lot of places you are going to see this TTFT, which is time till first token, right? So this is the time taken when you give a prompt for the first token to come. Now, why is it called TTFT? There's also something called TPS, which is token per second. Basically, how fast the model is generating these word tokens and how fast you're getting it. Now, you can just say TPS, right? why you have this new thing called TTFT, time till first token. Why is first token given so much importance? Perfect. Because of prefill. That's why you guys have seen a lag, right? The model like stops for some moment, जैसे तुम enter दबाते हो. It takes a little bit of time. That's when the prefill is happening. That's the reason it is slow. And that's why a lot of application actually monitor this specifically, called TTFT, time till first token. Because in UI UX, you have a lot of these things. For example, if your APIs are fast. So what you do is when you do a refresh, I mean, I think Instagram also faced this issue. The APIs were so fast, when people would refresh, it will actually refresh and then they will think refresh hua nahi hai. Right? So what they started doing is when you refresh, they'll show you the loading for 1 second or 2 seconds, right? So that you're confident, ha, refresh hua, right? So that's why this TTFT matters a lot. So time till first token, if it's very late, that's also something that people want to actually have a good TTFT value. And that's why jitne smaller models honge, jitne compute efficient honge, utna fast TTFT aayega, right? And this is also the prefill time. तो prefill भी होता है इस time पे, that's the time TTFT is actually calculated. Okay, and this is the wait time that you see in your UI. And then you have TPS. Oh, this we have discussed. The model weights are stored in GPU, right? The parameter weights, and then you can actually quantize these weights, right? Quantization we learned. Now you're decreasing the memory. But ab ek aur new memory is in picture. This is the KV cache, right? Now you can also decide how much you want to cache, right? How there are multiple caching strategies also, and optimizations done specifically to store cache in GPU so that GPU is actually utilized properly. Okay, and then depends on the batch size basically. So let's say I actually run 10 requests in parallel. So in my ML model, in my GPU, at every turn, the batch is 10 requests. So it will calculate the next token for 10 different requests, right? This is how it's going to look like. I'll show you later. Okay, so for 10 different requests, it's actually finding that. But then 10 ka, it has to store 10 request ka KV cache also, right? So you have to now decide ki how much parallelization you can do based on how much memory you have and all that, right? And that's why the KV cache depends on the batch size, and it's also GBs in size. So you already have like 24, 32 GB available, or 40 or 80 if you're using cloud instances. And then in that, you have to manage your model size also and KV cache also. Okay, guys, clear? Any questions? Perfect. So there's something called KV cache optimization. There are multiple algorithms for it. The one practically which made a huge impact is a library called Flash Attention. What the library basically does is, do you guys know L1, L2, L3 cache in your RAM? Your RAM is exactly, what is L1, L2? 3 cache? Close to it. Yeah, it's close to the CPU. So there are multiple layers to that, to your RAM as well. And CPU also has its own certain levels of memory, L1, L2, L3, and then it goes to your RAM if it doesn't find anything in all these caches. And then at the last, it goes to basically your disk to find it, right? In the same way, you have GPU cache levels. There's an SRAM and HBM. And then this is CPU RAM. You see the CPU RAM speed in that particular paper is 12.8 GB per second, which is very high. But then GPU RAM is 1.5 TB per second. And this is not even the best RAM, closed RAM available, right? It's SRAM, which is 19 terabytes per second. That's how fast it is, right? So these GPU levels. So what they did was this KV cache computation, this multiplication that happens, they optimized on it in a way that they are utilizing very well the different cache layers. And then this picture basically shows how this multiplication is done. What is this multiplication though? It's the attention multiplication. What's the attention multiplication? Have you seen it before? It is this equation, right? You have to take the Q, multiply it by K transpose, divided by dk, which is a hidden state number. This is a fixed constant value. You have to do a softmax of it, and then you have to do a cross product with V, right? So this whole computation is actually done up here. This is clear? Okay, and this is the Flash Attention paper. This paper was really famous because it optimizes your computation of KV cache really well. Another thing that it did was it can fuse multiple kernels together, right? For example, let's say if you have two different types of addition and you can find the common factor and stuff like that, you can do, right? A lot of maths you can simplify it based on how commons you take and all that. So in this way, kernels are also written in layers. You can fuse kernels and write the final simple logic and all. So they actually dig deeper into how these kernels are actually written. And these kernels are these mathematical computation, and then they fused and created the optimized kernel versions, right? So this is how they finally created a very good optimized cache formula, which is known as flash attention. So it's attention, the thing that makes LLMs, and flash is faster attention. Then there's also called page attention of KV cache. Do you know you delete your pen drive in like soft delete and hard delete? What's a soft delete and what's a hard delete? Yeah, right. Exactly. Yeah. So in soft, what happens is you just say that there's no data in it, where actually in those exact places in the hardware, the bits would be the exact values. And so basically a soft deleted pen drive hacker can see all these files because he knows that the data still lives over there. It's just that we tell the driver that this pen drive is empty, even though the bits are still exactly stored in the same way. And the hard delete is you take every bit and make it 0 or whatever, right? That's what a hard delete is. So basically, storage in these things are in chunks, right? So you always talk to your storage drivers, and then they have the underlying storage file system and all that, right? XFAT format, FAT32, FAT16, right? These are actually the block sizes. A lot of these times, these block size are wasted because let's say a small block size, let's say if it's 1 GB, you just want to store for the initial bits, then the next block would be from 1 GB to 2 GB, right? And so the whole portion in between is wasted. In the same way, you have like all these spaces which are wasted. So they also created a algorithm for it. They called it page attention, right? And then they also put page attention with flash attention, right? So this was something that they did, basically multiple things that they did to actually optimize on the KV cache. The storage in these continuous blocks also should get wasted because GPU expensive, right? RAM. And so they created something called page attention. So mixing all of this together. Now, if I will actually switch on KV caching using flash attention into my LLM, and then I'll deploy it, it would be 2-3x faster, right? Because my GPU is able to use the KV cache better, right? Clear? And then using it is also pretty straightforward. If you use some really good Docker containers by Hugging Face and all of them, they already have flash attention pre-installed into it. So the moment your LLM is taken, it'll have flash attention by default and it'll be faster, right? Okay. Okay, so I'll show you LoRa Exchange. For this, I would actually ask you some questions. Okay, so does anyone remember LoRa? We understood it before, right? You have one base LLM, let's call it Llama. You train small parameters, 5 to 10% parameters for my code editor project, right? Automatic code generator, whatever it is. I train those small weights. Now my Llama plus these weights creates actually a very good code writer. Llama on itself is a very good general model. I cannot train Llama because I don't have that much money, right? So you actually then take this, train the small weights, combine it together, right? Now, if you'll see, if I'll train another adapter, which does something else, right? That is sentiment generator. There's my another project. Then I have another adapter, right? In this way, you have multiple adapters for the same type of base model, right? So if you see over here, एक server का hardware cost that I have to pay, right, would be, let's say if I take a G5 X large machine in AWS, right, it's going to cost me $720, kind of like 60,000 rupees per month. In that, I'm deploying my Llama now. Now, this is my code completion wala project. If I have another project now, there's a new server, 60,000 paid again, right? So what I'll do is, but this is how it looks like internally. The yellow one, right, is my base Llama model. Okay, and this blue one is actually the adapters. Adapters we saw is just two matrices, but actually there are multiple matrices. Okay. So I just added my adapters in the model, and then it's the user one, goes for the blue one, which is actually let's say a code completer. The yellow one is another application. User 2 actually wants that application. So it's a new server. This box means a new server, right? And you keep on doing it every time you're running it on servers. What if you can actually use one server, run your Llama model, but then you can change adapters, or based on the adapters, you can give that user output of that adapter, right? So then you don't have to go for all these servers. You can just buy one server with multiple adapters in it. Why multiple adapters? Because I said one adapter is around like 5-10% or even less of the main model. So if GBs are loaded for the model, if GBs are loaded for the KV cache, then some GB would be for the adapters, right? It'll be in MBs though. And so you can actually load a lot of adapters. Now the challenge would be, once you have this server, how would you ensure that user 1 gets the model output multiplied by his own adapter weight? So user 1 is actually looking for a code completer. User 2 is looking for a sentiment analysis project. So you have to somehow make sure that the base model is the same, different adapters output is given to that particular user. To do all of this, first of all, like this is called LoRa exchange in one of the libraries called PEDibase. And basically this is multi-LoRa adapter. We call it multi-LoRa adapter loading, right? And in this, what happens is multiple adapters are loaded, and then you can, with one server, have actually multiple versions deployed. Ye clear hua? No, we actually load every adapter. So if you see over here, we load the yellow one as well, the red one as well, but the user one will get the multiplication of this with the blue one and not the red one. You do something called masking to be able to do it, but the user one only gets this one. User 2 gets this one plus the red one ka output, which is actually the fine-tune adapter for that particular problem, right? And in this way, you have user 3, 4, 5, you load multiple adapters together, you get the output, right? And your one server can now serve multiple different LLM applications. So that's huge cost saving, right? नहीं, लिंक होता भी नहीं है. No, that's cross linking. ऐसा कुछ नहीं है. I get your point, but like even one comma change or full stop change are two different prompts, right? I mean, like, and then both users are different, yeah. It's a way to be able to just have one server and be able to give fine-tuned models to everyone, but just using one server, not every server for a fine-tuned model, right? So in a way, you just save on the number of servers you need. At the end, the algorithms are written in such a way that they will do all of this for you. You just have to run those adapters, mention the list of adapters. And while calling the LLM, you can mention that I'm actually looking for adapter 1's output. You have to mention as a client that I'm looking for code completion wala adapter ka output, right? Okay. Clear hai guys? Thoda yahan tak. Okay, so now isme bhi optimizations hote hain. So you have these time cycles. So every T1 is a decode phase. LLM decode matlab next token generation. So S1 is first prompt. First prompt ke tokens hai. S1 has 3 tokens, right? And so this is a longer prompt, this is a smaller prompt, right? Prompts ke bhi different size hue. And then you'll batch it together. So if you batch it because you have those RAM available, you batch these queries, you put it into GPU. And when you'll now generate the next token, so for S1, the next token would be the 4th one, S2 ke liye the 3rd one, right? And so on and so forth. Now, when will you stop? You will stop basically processing this batch when the longest output, the blue one is the outputs that are generated, when the longest output says end. So all of your queries actually give an end. This is the time you're like, okay, all of my queries have completed. These are different questions asked to, let's say, ChatGPT, whatever it is, right? Your Llama deployed model or whatever. And then this is the time you take all the answers and then you give it to user. So basically, if I am third user, S3, I'm actually waiting until S2 is complete, right? Even though over here you can see that at level 5, my output was complete. At this time in itself, I could have got the answer. But now because this whole batch is loaded in GPU, I have to wait for user 2's end as well. This is the latency that I'm suffering, right? Because of other users. So this is also something that was optimized on. And that's why this method is known as static batching. These then servers were optimized on continuous or dynamic batching. What this simply means is, when let's say you have these multiple queries, at T6, when the first query ended, right? Rather than not running anything over here, why can't I just simply load, my next query, the query X6, so that in next token, it will also start generating the output for S6. Why can't I stop in between? And then if a particular row's output is complete, I take that request out, I give it to that user, and then I put some other request in, right? So these things I can do. So this whole algorithm of like manually taking requests, taking them out, and all of that, this is what continuous batching is all about, right? So you are not letting other users suffer because of long queries by other users. You're smartly actually stopping in between and seeing how many queries are complete, taking them out, filling it new ones. When you fill a new one, then also there's a problem. Her query ka first fill will actually call its prefill phase, right? So her query ka first one is also going to slow everything down because now a prefill is going to happen, right? So you can't just at every stage check all of it and then put one, because then it will go through a prefill, then everything would also get slow. So you have to find a really nice balance between how, or like when to stop, what should be the ratio. So these ratios are different based on like what kind of application you want to make. These things actually differ. But basically, this is the whole crux. You utilize this taking request out, putting it in all that, which also increases your TTFT as well and all the other matrices, right? Okay. Exactly. So वो depend करता है. T5 में end करके if I'll put a new request, prefill का time जाएगा, which is also suffered by all my users, right? And so I can also end it key, okay, let's end after these cycles and check. Now this end after exact 2 tokens, the blue ones we cannot predict, right? How long the query would be. We don't know yet. So some would be like 2 tokens, but the output is so long because the 2 tokens were kind of like write a essay on Shakespeare with like 100 words, right? And that's why you have to decide when to actually stop, take request out, put it in and all that, right? So, but basically this is also done to speed up your servers, your LLMs. Clear हो रहा है थोड़ा थोड़ा? So if you'll see, your GPU has a fixed memory, right? You can simply calculate how many parallel requests I can put in, right? So this is the number of tokens generated per second. अब token generated per second के बाद भी every user will have very different experience with your LLM. Why? Because if you have static caching, even though your server is fast, someone's query is slow, you are getting a slow experience, right? So it doesn't mean that even if you have faster servers and all of that, you get the same result, because the dependency is there. Now it depends on the function of what different people's queries are. And so you do something like this, continuous one, so that every user also feels the speed because if their query is done processing, it gives the output as well, right? And so everybody would now be able to get the answers faster, right? Because it doesn't actually wait for the query to end. And then also the good thing is, up until this point, if you see, S5 cannot be added in static caching. So all these blank ones could have been actual computation, but it didn't happen, right? Now over here, you can see I've put S6 as well. So my TPS also increases, which is the total tokens processed per second. If you will see, the number of boxes are more, right? Over here, which means more tokens are processed per second. So my server has now become faster as well, more responsive as well. That's the optimizations that we have done. Clear, guys? Next, chale. Okay. So now to do all this, the way these servers can work for you is they will automatically load the adapter when it comes. Dynamic adapters, basically, the storage could be on CPU RAM or the GPU RAM. And when a query comes, it can load that adapter, generate the output, give it to that person, right? So that's like the dynamic adapter thing. Then we have at runtime offloading of adapter weights to CPU, avoid memory out of errors. So a lot of times these adapters can be put into CPU, can be brought back to GPU, and then, based on if some user is not using it, why to put his adapter and do the computation? I mean, it won't even be used, right? Because all the adapters have to be placed in parallel and then computation has to be done. So automatically they are taken out if it's not used and all of that stuff, right? So basically you have server implementations written in which you can mention all your adapters, right? And then the server will take care of adding these adapters to GPU, getting the output, giving the output back, taking these adapters out, putting new adapters and all that stuff, right? Okay. Fine. I think, Abhi, till this point, does anyone have any doubt? Questions, anything? Okay, we will not dive too much deeper into Kubernetes, right? Even though like there's a lot of stuff which is created for Kubernetes in these PPTs, but we'll just get to know some very simple things. Let's not like deep dive into Kubernetes and like all the things. But I think in some cohort programs also Kubernetes was taught, right? But in general, we'll put this as like introduction to Kubernetes. We'll not deep dive into all these things, and we'll just simply show you that this is a Kubernetes deployment. This is how it looks. This is how everything is done. There's a project created now, and we'll just see it in action. Kubernetes may deployed, right? All these LoRa weights, how this works, and that's simply it, right? So in all these PPTs, if you don't understand much, that's also totally fine. Okay, guys, start kare. Up until this point, any questions? Okay. Okay, so the thing with managing containers is you have these Docker containers. I'll skim a little bit faster, right? We are increasing the speed as we talked, right? So yeah, I'll just say that there are Docker containers. You have Docker containers deployed. Then what happens if a server dies, container dies? It takes the whole application with it. So you actually run multiple versions of it and you put it under a load balancer. So this is a load balancer. If this Docker container dies, the request goes to the next one, and so on and so forth. Okay. Now what Kubernetes does is, let's say these two Docker containers were on the same machine. If the machine dies, these two containers would also go with it, right? So now you have multiple machines, and in each machine you should have multiple of your Docker containers load balanced together. So if the VM goes down, still your application is up. If your Docker container goes down, still your application is up, right? Now what you're going to do is, this was one application. You might be having multiple microservices or multiple applications. So now all the multiple applications load balance separated in all these VMs. So a lot of these things has to be managed, right? And what if it wants to scale up? When it wants to scale up, it needs more VMs as well, right? You cannot crunch everything in your 5 servers only. You might want to add a new server. How will that happen now? You need another server, right? You have to add it, run these containers, put load balancer over here. So all of this is, there are multiple things by which you can manage it. But one of the tools that can simplify it for you is Kubernetes, right? So in Kubernetes, all you want to do is, you say to Kubernetes that these are my set of nodes, my VMs, and you can also give it permission to add more VMs if it wants, right? You're actually paying for the number of VMs you're using, and in terms of using means you have switched it on. If you use it internally or not, that's not the thing, right? You have switched it on, it's being used, it's been given to you. That starts the billing process, right? Now what you can do to Kubernetes, say to Kubernetes is, if there are more containers, get a VM for me, run those containers up. If less traffic is there, take, and no containers are running on it, give it back to AWS, switch them off, terminate, right? And that's how Kubernetes can automatically manage your loads. All you are now doing is saying that, hey, my Docker container needs this much CPU, this much memory, please deploy it in one of the servers, right? Then Kubernetes takes care of deploying it, scaling it up, managing it, and all of that. Guys, clear it now? Simple, right? There are a lot of features to Kubernetes, and Kubernetes is like a very popular thing. So initially, Okay, there were a lot of tools created which actually did what Kubernetes does at that point. And Docker was also not a totally new generated new idea that was like, oh my God, like containerization, it's such a new thing. Before that, there were also a lot of implementations of Docker, different ones, which were popular as well. And Kubernetes, there were also a lot of tools which did the same thing. But Kubernetes and Docker, the thing they did was they really made it very easy for the masses, right? Like present day mein ek Docker container create karna is so easy, right? That ease of development and working with it is what made these things very popular. So Kubernetes was actually created by some engineers at Google. Google had a Kubernetes-like stuff called Bok. Present day also Bok is being used in Google. And these engineers actually liked Bok, but they thought we can do something better, right? They created something called Kubernetes. And the Google team actually didn't like it initially. They were like not ready to take this project forward. They wanted to open source as well. If you want to open source on behalf of Google, then also you have to go through an hierarchy of permissions, right? That you are now representing Google in a way. And so they also took it to the management. The management also were not very much interested, but eventually they finally got a positive flag to actually green flag to actually launch it. They launched it, I think in DockerCon or somewhere they launched it, but quickly it gained popularity. And then the thing was a lot of enterprises were not accepting Kubernetes because Kubernetes was new. They didn't actually rely on it, right? You don't want to put a banking application on Kubernetes if Kubernetes is not tested back, right? Right? You're actually scared the users won't get a good experience. So one of the biggest application success, which actually made Kubernetes so popular and made it really famous that it's very reliable, is an application I think you would have downloaded. It's called Pokemon Go, right? So Pokemon Go was super viral at that time. And so much load was actually generated to actually deploy on it. A Pokemon Go, उस time पे इतना high concurrent traffic था, and then they actually used Kubernetes. The people I think at Akamai or something, they used Kubernetes, and Kubernetes did really well. All the handling and everything was super. And then this was one of the biggest production implementation of Kubernetes, after which it was like, this thing works, it's amazing, let's just work more on it. It got super popular. Now it's one of the biggest open source projects that we have, right? Kubernetes is super huge now, right? And that's why it's used. So generally for DevOps engineers, Kubernetes is kind of like, now it's kind of like a must have. If you want to be a DevOps engineer, then you should probably know Kubernetes. Okay, right? So there are a lot of features. Fully managed application lifecycle. My application whole life cycle, when should it be restarted, deleted, created? I can just mention it, right? Kubernetes will take care of it. Easy microservice communication. My database server wants to connect, my backend server wants to connect to database, but they are on different VMs now, remember? So now the communication can be made easy. So that is what Kubernetes does. Role-based access control, who gets access to what in Kubernetes is very well defined. You can actually change it. Auto-scaling of containers and node. So if the application load increases, increase more Docker containers. If needed, increase more VMs as well to put those Docker containers in. Automatically scale it up, scale it down. That is also what Kubernetes does. Okay? Third-party plugins. Now, anyone has worked with Nginx, right? It's a load balancer. Now, to be able to seamlessly integrate with Kubernetes, there are a lot of Helm charts or Nginx community managed files, which you can just simply install on Kubernetes and it'll work because it's open source, right? So a lot of third-party plugins are written, which makes your life even more easier. And then you have other features as well in Kubernetes, like cron jobs and all, right? Has anyone written a cron job, right? So if you want to run something again and again, you create a cron job out of it, right? Your process runs the cron process, and then it finds out that it needs to run that code. It'll run on any particular given interval that you have. So these kind of features are also in Kubernetes, right? Where you can also mention these things, and in some node, your container would run and then would be discarded. So a lot of features basically is what Kubernetes gives. Okay, so this is what we'll skip a little bit quick. Don't get overwhelmed by all these diagrams. But the thing is kind of like this. You have the user, the container it's talking to. These containers can talk to each other in an EC2, right? And then this is EKS, which is, so now Kubernetes is open source, but all cloud have created their own modified versions of Kubernetes. which works better on their cloud environment. So AWS has EKS, Elastic Kubernetes Service. GCP has GKE, Google Kubernetes Engine, and anyone knows what Azure has? AKS, perfect, right? Azure Kubernetes Service, I guess, right? And so you have different servers. These servers connect to the EKS control plane. So it's kind of like there's one master, one primary node, and all the secondary ones actually talk to the primary and give them the updates, right? And then on all the worker nodes, there's a service running which is known as kubelet, which gives the main master all the information about what is happening on that server. Is the server healthy? Does the server has RAM and GPU available or CPU available to actually run the container, right? So all the time you're actually talking to this EKS control plane, and then EKS control plane gives information to kubelets that, hey, deploy this over here, deploy that over here, right? And then kubelet will do all the part. So kubelet runs as another daemon process, right? It will then run your container on that particular node, and then all the networking is taken care by Kubernetes, right? So this is how basic architecture works, right? So we have something called pod in Kubernetes. Basically, rather than saying Docker containers, pod can be multi-container, but pod is the smallest unit that a Kubernetes cluster understands, right? And inside the pod could be multiple containers talking to each other as well. Yeah, then it also has something called as deployments. Basically, what you want to do is you have a load balancer. You have one application over here, right? But that is the application version 1. And then all these load balancers, all the load balancer does is sends the request to the first one. Now my V2 is coming off the application, right? So all these 3 Docker containers have to be replaced by version 2, the new container. The problem is that old ones are still running. If I'll switch it off, my application goes down, right? And I don't want to take all these containers out and then put the new one. What I'll do is something called a rolling update. And then there are things also recreate. If your application is dependent in such a way you want to remove everything and then do it again, you can do also that as well. But this is one way in which Kubernetes manages is something called deployment. To the deployment, you say that there's a new version of my application. What deployment does is we'll create another container. We'll now start sending requests to this, and we'll start blocking requests to the old ones. But it'll be a smooth one-by-one process. It'll create another one, start removing another one, and after a certain time, V2 is the only Docker containers that's working, right? And when it removes the connection or request, it just doesn't give new request to that container. An existing request is still running, right? You give certain time for the container to actually die, and that time the requests are processed is what you assume. And then you actually are on version 2 of your application, right? So yes, slowly you can do it in Kubernetes. The other feature in Kubernetes you have is something called service. Basically, if 2 apps want to connect to each other, right? Let's say inside Kubernetes, you have a database called Postgres, and you also have your backend application. If you want to connect the backend application to Postgres, now where's the Docker container? Is it on the same machine? Maybe, right? It's on different VM, but in different VM, is Postgres only one container? No, it can be like 4 Postgres containers because you have like load balanced it, right? So now when you actually want to call your Postgres container, where would the networking be? How would it happen? So Kubernetes basically takes care of everything. You create something called service, and the service name, let's say my service name for Postgres container is Postgres. So what I'll do is I'll call my Postgres port. You know what Postgres port is, by the way? Perfect, nice. So I'll call my Postgres 5432 port, the default port, let's say, and then it will automatically, Kubernetes will figure out where the Docker containers are, and also will try to round robin or whatever the strategy is. It will not send all the requests to only one container of Postgres. It'll also try to balance it across different nodes and different containers. It can be anywhere, right? Kubernetes responsibility is to take that request and put it to the right VM and the right container, right? So this is how the service thing is. You can just create a service, and then the service would just enable networking. You can just call it. So HTTP, it's not HTTP. Postgres has its own protocol. So it'll be like PSQL, the name of the service, which is Postgres 5432, and you provide your credentials or database name and all. Okay. Yeah. So this is how Kubernetes thing is. See, this service can call this deployment. You remember deployment was one version of my application, V1. I created a new deployment version, which was V2. Then the old deployment was removed. It's actually replica set, but let's call it deployment. New one was created. So see, I have my front-end deployment. It will talk to the backend deployment using a service name. And the service will take care of this request being forwarded to any one of these three pods. Then the service request can talk to the database deployment, the backend, using another service in between. And this service will take care of sending the request to that particular Docker container. The container obviously can be anywhere in EC2 and can also have multiple copies of it. The service takes care of that. So this is how microservices are created. Each service in its deployment, services talk to each other using each application in its own deployment. Each different applications, microservices talk to each other using a service in between. And this is how microservice communication happens. थोड़ा थोड़ा समझ आया, right? Gist आ रहा है. If you'll take a good Kubernetes course, you'll just understand everything. But for now, I think even this, just by knowing like what services and deployments are in Kubernetes is also good enough, right? Okay. Any questions? Continue, kare. Yeah. Perfect courses, Mumshad Manambed, Kubernetes course. Like it's the best. It's also on YouTube. You can also buy it from Udemy if you want. Mumshad Manambed. So his Kubernetes course is perfect. And it's a 2-hour, he has a 2-hour Docker and 2-hour Kubernetes course, which is all you need to know if you want to deploy your application on Kubernetes. And then obviously Kubernetes is complex enough that you would just have a lot of things elsewhere. But those 2 hours on Docker and Kubernetes are good enough that you can start deploying stuff on Kubernetes. And then you can take it from there, create your own applications and all that. Yeah. Yeah, I'll search it for you then. Wait. Yeah. So it's Kubernetes for the absolute beginners by Mumshad Manambed, right? So you have you. So you can take this one. But yeah, okay. It's fine. I'll also share it with you afterwards. ठीक है? Continue करें? Okay, great. So autoscaling in Kubernetes, we discussed autoscaling, right? It's not just Docker that we want to scale. We also want to scale the EC2 machines. There's something called in Kubernetes known as horizontal pod autoscaler. बस इतना याद रख लो कि if there are pods, उनको अगर scale करना होगा, so HPA does the scaling part, but how does it know you have to scale those pods? You tell it some rules that if my CPU, average CPU utilization of all the containers goes above 60%, which means there's a high chance it will cross 100 also, and my server will die. So at 60%, add more servers and load balance it. So when the average goes above 60, add more servers. If it goes below 60, remove servers. Because now obviously your traffic is going down, you want to remove servers, Docker containers. Why? Because if you'll remove containers, these VMs will also become free. So you can remove VMs also. Removing a container doesn't mean you're removing the VM as well. And you're paying for the VM, right? And so just like HPA, there is a cluster autoscaler. What it does, if there is a node which is empty, doesn't have containers, remove the node from Kubernetes, right? And then terminate that node. So basically, this is what it is. These small kubelets tells what's the status of every node and every pod inside that EC2, right? And then they give it to something called a metric server. Metric server gives it to metric API, which gives it to HPA. Basically, HPA now finally gets to know what's actually happening in the whole cluster for that one application. And the Kubernetes admin has given it instructions that for that application, if it goes above 60, then scale it up, scale it down. And then what it does is it calls the deployment and says it that scale it up by 1, scale it up by 2, or whatever strategy you have, right? So this is what HPA is in a nutshell. Clear here? Right? Okay. Nice. Okay, finally, let's see something in action, right? कुछ project देखते हैं. I would not go too deep into the code, but does anyone of you guys know what load testing is? Yeah, nice. Okay. Yeah, yeah, right. Exactly. So I think someone asked, right, ki how many servers should I have to finally host my application, right? The thing is, we don't know. The application has a lot of things. So what you do is real world testing. See, Christmas, New Year, and all these times is what Facebook's ke engineers ke liye is the highest peak moment 2 months back. Why? Because they are load testing all these things. They don't want the whole Facebook application to go down, right? That's what Hotstar has done. Concurrent connections, do it beforehand because live day, match wale day, agar kuch problem ho gayi. So we don't know. Now, how would you know कि वो system उस दिन चलेगा कि नहीं? I mean, you can't pray, right? कि system should work. What you actually do is you create virtual users who would like, what does a virtual user do? It's actually a program which will run the same thing. So it will like log into Hotstar. It will then start a streaming of a match, live match. Or maybe it'll start watching something else as well, right? It'll do random behavior, but it's through code. You're creating one virtual user. Now you can just multiply it as much as you want, and you can then simulate 10,000 users, right? So then you take this 10,000 user simulation and then you run it through your application just to see ki mera application, how good is it scaling up or scaling down, right? That's very critical. So you do some real world testing. And what's a black box testing is basically you don't know what's inside the application. You're looking it from a far end. We don't know what's inside Hotstar, right? The backend. We're looking at it from a distance. We are behaving as a virtual user. We are just using the product and we are seeing the metrics, how good they are doing, right? That's what the black box testing is all about. Clear, guys? Okay, so load test is very important for my application. If I have, let's say, if I assume 5,000 people would be using my application, I'll create 5,000 virtual users using my application in the exact same way with all the randomness and everything. I'll launch those 5,000 once. Then I'll get to know some very good metrics. How much time does it take my app to actually respond for TTFT, time till first token? So what would every user get an experience by when using my app, right? Because when you are using it, everything is fast. 5,000 users using it, you'll actually know, oh, it takes 20 seconds to actually get the first TTFT. Because like 5,000 users are using it, the server is now bombarded with that service, right? So this is how you do the actual testing, right? Let's look at a little bit of code base, right? We'll skim really fast through the code base and I'll just show you the final stuff. But what we have in the project is we have a Kubernetes cluster. Now this Kubernetes cluster has HPA in it, horizontal pod autoscaler, to automatically scale the servers when there is high load. That's what we are testing for, right? We're not testing for output. We know the application gives output because we have done it. We now want to actually see in real world scenario how good it is doing. So we want to see the auto scaling of the application in load testing, right? And it's not just auto scaling though. A lot of the times you won't realize that your application has memory leaks in it, right? So memory leak ka problem is ki when you're testing, it's fine. If you keep the server on for 5 days, the memory keeps on increasing of that server. And then eventually your application dies. So there are a lot of other errors also that you want to check for. That's why there are multiple types of testings that you have to do in the application in production to actually ensure the output is really good. Okay? So what our project would be that we will have on AWS a load balancer. A load balancer will then have a Docker container called Locust. So there is a Python library called Locust. In Locust, you can create virtual users, right? I can't tell each one of you to install Python application and call this endpoint, right? So I'll create a virtual user. That virtual user, what I'll do is I will create a multi-LoRa project. I'll show you that. And then you'll give the virtual user an option to first spin up, wait between, let's say, 2 to 10 seconds or whatever. Just try to behave normal. I mean, you just don't open and do it in milliseconds, right? You also look at places 2 to 5 seconds. And then we'll say to choose between one of the LoRa adapters. So either try to be a named entity recognition. So what is an NER? Given a passage, you can answer things like places. Places are in that passage, like London or whatever. Names could be exact names. So this is what named entity recognition is. Another adapter we have is Coder, which is you tell it to write a Python code, it runs the Python code. The third one we have is a customer support engineer. So given a customer query, it can know that it is related to payments, it is related to technical issues or whatever it is, right? You have to categorize really well. So you have trained that LoRa adapter to categorize really well for the given input. So these are three different applications, but you are actually running it on one server using multi-LoRa, the thing that we discussed, right? And so this is the LoRa container, multi-LoRa container, having all that. And these are adapters. Every adapter is trained for that particular data set, right? Those three applications. These are adapter which are loaded in real time from Hugging Face. And the model is also downloaded in real time from Hugging Face, right? And then this is my Docker container where my application is hosted. This is my Locust application, which means my virtual users. I mean, at the end, if you're creating 10,000 users, that Python code will run somewhere, right? Those 10,000 users would be created. Where would it run? I'm just running that also in Kubernetes. Well, actually, you should try to run it somewhere else. But in this one, I'm just running it on the same server. And it'll create all those users in parallel and will bombard the application with these requests, right? And every request could be any one of these three output that it's looking for. And then HPA would start to monitor that. A lot of load is coming in, I should scale up, right? Some metric is being breached, I should scale up the application. What will it do? This is a different deployment. LoRa deployment is different, Locust deployment is different. For LoRa, I have written that if the average of all the LoRa containers goes about 20%, scale up the application. If it goes below 20, scale down the application, right? And so this is how the GPUs are also there in the machine. HPA will increase. These numbers of LoRa containers will also increase. They will automatically be load balanced as well, right? And then you would see the changes in the time it takes for the request to work. Guys, project is clear, right? Okay. We are using multiple things that we have discussed up here to be able to run this project. No, thank you. Wait. So let's look at the code. I'll just remove my keys anyways. Yeah. Okay. So we have EKS in which, so everything is done through YAML files, right? We have a declarative based stuff in which we just say Kubernetes do this. We don't say exactly, run this code, then do this, step 1, Docker this. We just say this is my end state, go to that state, right? So this is what service looks like. I created a service. Ingress is basically the load balancer in AWS. So I'm just saying that the load balancer should be internet facing, right? Don't get deeper into this. This is very simple YAML files. If you would be studying Kubernetes in depth, you'll get to know what this is, right? I'm just creating a load balancer. Now creating a load balancer is so easy. In Kubernetes, you just have to mention this. The load balancer automatically gets created and gets attached to the service. Service automatically gives it to all the load balance containers, right? Right, there's a secret. This is my Hugging Face token, which I'll delete later on. But this token allows me to download my model and adapters to be able to use, right? Okay, this is my deployment. There are two deployments. One is I'm deploying LoRa with this image, right? This image is on Google Container Registry, right? So it'll download it from there. And my Hugging Face token is also given to it, right? And then, yeah, some CPU and memory is given, so it's fine. Nothing major that we have to discuss. Now, this is where HPA is. This is the file that you have to give to HPA called horizontal pod autoscaler. When you give this file, you can see my deployment name is LoRa deployment, LoRax deployment, right? It's not Locust. I don't want Locust to scale up and down. I just want LoRax. So it's called LoRax deployment. It tells it to search for this deployment name. And you can see the CPU utilization, right? The target CPU utilization, if it's average 20, it's above that, scale up. Below that, scale down. So these are some of the things that I have to mention. Now let's look at the load testing framework. The Docker container, the Locust container, which is there in my Kubernetes, right? How does that look like? So it's a Docker container that runs this Python file. So you can see how easy it is to create virtual users. I will subclass the HTTP user. And then I can just mention that wait between 1 to 2 seconds, right? And then I will have 3 different tasks. So I have task 1, task 2, and task 3. The application would choose any one of the tasks at random, right? So the virtual user has freedom to choose any one of the tasks. First task is call NER recognizer, which is like find out the names, then customer support, then code generator. If it goes to the NER recognizer, see, this is the adapter name. The client actually says, I want output of this adapter. You have to say it from the client side, and then the server actually runs that adapter and gives it to you. So that's the adapter path, right? Pretty base. It's actually downloaded from Hugging Face, right? So you can also see it in Hugging Face. So if I'll go to Hugging Face, I can say that I'm actually looking for this adapter. See, this is how adapters looks like. Okay. Yeah. Okay. So my adapter, it will tell you all the things. See, you can see the PEFT tag over here, parameter efficient fine tuning, right? So which can say it's an adapter. You can see the files and versions. It's a adapter model with an adapter config. So in this way, this is not a model. This is an adapter, right? For a model. What's the model of? You can find more over here. What was the data set this was trained on? That's also mentioned, right? LoRa land, and somewhere down, this is also mentioned over here that it's a Mistral fine-tuned model, right? So you only use this adapter with Mistral. It will only work with Mistral, this particular one, because during training time, we use Mistral to fine-tune it, right? And then it was trained on this data set. So automatically, the container will load it at runtime if a user calls for this particular application, right? Exactly. ये फाइन ट्यून हुआ था इस डेटा सेट पे मिस्ट्रल मॉडल को फ्रीज करके. ठीक है, तो you should use it. अब I can't use my Docker container, and in my Docker container I have to also mention the model name. You see, the model ID is Mistral 7B instruct v1, right? The reason is because my adapter is Mistral 7B v1. Clear, guys? All three has to be here, right? Okay, so now you'll see that the locust file, the locust.py. See, this is my question. Your task is a named entity recognition task. Predict the category of each entity. We also learned something called example-based thing, right? Few shot prompting and all stuff. So yeah, there's a question up here. EU rejects German call to boycott British lamb, and then it automatically recognizes organization is EU, location is this, miscellaneous Germany, British. You're actually giving LLM an example to actually, get the next examples in your way, right? Prompt engineering, basically. So then you give the final input for which it has to generate the output. Now, how would we know that the application is working correct? We already know what the expected output should be, right? For this input, is it visible? Okay. Let's ignore it. Okay. So we know for this input, I need this output. So what we'll do is we'll call the URL of the LLM, the generate endpoint. In the input, I'll give my prompt, right? These are the hyperparameters that we discussed, right? The temperature, the top P and all. This is the adapter path. I'm giving as adapter ID that I want the output using this adapter, right? And then obviously, if you're asking an NER question, you want the NER adapter, right? And then you get the response. If you get the response, convert it into JSON, see the generated text key, and check if the key actually matches with the expected output. If it matches with the expected output, it's a success, right? If it doesn't match, count this particular call as a failure, right? And so you just simply count it as failure. You do the same thing with call customer support. You want to know if a question belongs to replace card, transfer money, check balance, or what. You give it some input. You already would call it, but this time the adapter would be different. The adapter is customer support adapter, right? You'll get the output. You already know for this question, the check balance is the type. And so I'll do the same thing, true, false. And I create the third one in which I'll give complete this code. right? So it's a magic coder predibase adapter. Because my temperature is 0. Yeah, but like if you fix it, this is the rarest of the rare case. Like, 99% of the time you'll get the same. I mean, even more than 99. But it's just like I want to make sure that, you can't be 100% sure. The determinism is not there. Okay. No, you can't decide that. It's actually a limitation of this hardware and all that, right? They're managing multiple hardwares and the random numbers are also very different. It's like it's very hard to actually be very deterministic, right? So it's a problem of that. You can't solve it basically. I mean, it's not solved right now, right? Okay. So you have this three. Fine. Where is this Docker container running? Kubernetes. So let's call this Docker container, right? Okay. So the Docker container is actually deployed through a load balancer. If you remember, this is the load balancer, right? So this is the address of the load balancer. So let me open it up. I have HTTP enabled. Okay, so this is how it looks like. Let me just refresh it. Okay. Fine. This is how Locust looks like. You can create a new test. You want to mention number of users that you're looking for, right? Let's run it with 50 users, right? And you want to ramp up. You don't want to launch 50 users same time. You want to slowly add five users, right? Let's just keep it like 70. Every second add 5 more users. Or let's do it slow then. 2 users, right? And then this is the host, basically where's the LLM address, right? So this is the LLM address. This is still this, but the DNS value is different, but this load balancer is the address. And then basically you call it. And then it runs. Now you can see how many requests are made, how many actually failed. What is failed? Your expected output didn't match. How many were success? What is 95 percentile? Is 95% of your application actually would respond in less than this time. 95% of your request, right? 99% of request, if I am going to create a code generator, will actually respond back in 11 seconds. Right? These are all these metrics. Now, if you see here, these are the charts for it. So these are the charts generated. Now, if I look at HPA, right? If I'll do a watch, CTL get HPA. Okay, now you can see the target utilization has gone up 50, right? Pehle, it wouldn't have been 50, it would have been 0. And then you can also do is check the number of pods, right? Previously, the pod was 1. Now the pods are 2, right? If you see here, initially the pod was 1 because the age of the pod is 12 hours, right? If you'll see here, the age of the pod is 60 seconds, which means it just started now when you actually started bombarding the application, right? And it is still not in ready state, which means it is still downloading the model, putting it into GPU, starting up, will start serving the request, but it is scaling up basically, right? HPA has created a new pod, it is scaling up. Now it will take some time to actually scale up, but when it will, you'll see a drop in total time because now the whole request is shared between 2 of them, right? And so you'll see, so this is the total request per second. Per second, there's like 3.5, total 70 users are there. The response time, you can see, it's just increasing a lot. 25 seconds is what average response time it takes. You can see the stats for your different application. And in this way, we are load testing in real time how the application performs. This is still warming up. Maybe it's downloading the whole multiple GBs of weight, right? Of Mistral, and has to load it, put the adapter as well, and that's why it's taking some time. You can also look through the logs in Kubernetes, like what's happening inside. Right, and these are the logs in real time. Okay, I think I logged the wrong one. Yeah, see, now 1 out of 1, which means it's ready. And can you see the total time decreasing now, right? It was up, now it has started to go down. Hmm? No, the response times over here. See, it has started to go down now. Yeah, the TPS will increase because now the total request, number of requests that can be handled actually goes up. But you can see this drop coming in now, right? That the 50th percentile time, the 50% of application time actually started to go down now, right? Yeah. And the number of users are obviously 70 concurrent users, right? So now your application has started to scale down. Scale up, and your metrics are increasing. Okay, so I think this is it, guys. Yeah, I think this was an okay refresher of what LLMs are, how they work, how they optimize, how we can deploy, what Kubernetes is, how we deploy it, different optimizations we can do, right, to save on cost and everything. So yeah, this gives you more or less like what LLMs are right now. You can now search more, dig deeper, work into training and other stuff, and you can start working with it. Okay, thanks.